I'll pass it on to our next speaker, Alp. Please give a round of applause.
Thank you, Gabe. Okay, so hi everyone. Thank you for coming to my talk. I'm Alp. I'm a fourth-year PhD student at University of Maryland. I have been working on property-based testing for the last 4 years, and I have some thoughts on that. So let's go into the nitty-gritty bits of property-based testing. Like within the talk, I'll first very briefly introduce what property-based testing is. I'll not go into a lot of details on that part. And then I'll talk about what property-based testing libraries do, how they do it, and some papers that are trying to make it into the next generation, move property-based testing further. And I'll just give some conclusions and leave the stage. So to introduce what property-based testing is, let's start with a unit test. In a unit test, we have some input-output example, right, that defines some behavior in a concrete manner. So here we see that a list that contains 1, 2, 3, if appended 4, is going to end up to a list that is 1, 2, 3, 4. And for a property-based test, the first thing we need is a property. And a property is simply an abstraction of the concrete behavior we see here. And this concrete behavior might be lending itself to multiple abstract properties. One of these could be that the list contains the appended element, or it could be that the resulting list is going to have a length of +1 with respect to the original one, or that the last element of the list is the appended element, or that the prefix of the list doesn't change. It is actually sufficient to have the last 3 to define the behavior of the list append fully. So that's what a property is. But how do we test it? How do we use this abstract properties to concretely test our system? And the way we do that is, here's a simple illustration. It has 3 components right now. It has the generator, it has the checker, and the printer. So the generator is in the previous slide, I have shown you some for all, like for all lists and elements, appending a list to an element increases by 1, right? So we need those lists and elements. And a generator is simply a function that gives you some of those things. So it gives us random lists and random elements. And our checker is a function that executes the property. For a given list and an element, it actually appends the element to the list, and it gives us the returning list, and it checks the property to see if it's correct or not. And if we get a counterexample at the end, we might fail, right? But if we get a counterexample at the end, if we find a violation of the property, then we would like to also print it. So what we do in the process of property-based testing such a function is we generate, check, generate, check, generate, check until we reach a counterexample, or we give up, and then we print whatever we want to do. So in Python, a very simple version of this could look like version of a property-based testing loop could look like this. You have a function with some maximum amount of tests you want to run, and you run them. You first generate, you check, depending on the result, you continue, or you just print the result. So this all looks very simple. Like when I first about property-based testing, it looked to me that like, okay, this is so intuitive. We should all do it. But there is this question, what do we really need libraries for this? Like, isn't it just too simple to do? What does a property-based testing library actually gives you? So this is the point where the talk stops for a minute and you guys think. And if you have any like ideas on what like if you're using property-based testing in your daily life, if you're using it in your work, what do you think the library buys you? I'm going to give you like in 5 minutes, 10 different examples of what I think the libraries buy you. And maybe I missed some of those things. So like, does anybody have any thoughts on that? smarter way to do random generation of inputs. Okay, so that is one of my points. Nice. Yes. Shrinking. Thank you. Okay. So before I spoil the rest of the talk, let's continue on that. The first thing I think what the library buys you is modularity. Because when you're writing tests, you're not writing one property test, right? Like you're writing a lot of these tests. So you want as much reusable component as you can have. So the first thing that the library gives you, of course, is like integration with the testing framework of the language and so on. But it also gives you some default generators for the like canonical types that you have. And the second thing is it gives you in that regard is the combinators. So one-off is a generator that takes a list of generator and randomly picks one of them. So we can think of these like higher order generators. And frequency does the same thing as one-off, but just it does it with respecting the frequencies of each of those generators. And our generators can actually backtrack sometimes. So if you use they can actually fail sometimes. So if they can fail, you can run multiple of them until you find one that succeeds using backtracking. The second thing that the libraries give you is the properties are not really booleans. I lied to you earlier. So if you think of the example that I had shown you, for all lists and elements, appending an element to the list contains the result, contains the appended element. This property is correct. So like this is a Boolean predicate. This is going to be true or false, yes or no. But the problem is though, is the property itself always valid? Because sometimes there is no, you don't even want to check the property because the initial state isn't even valid. And this here, it says, if the initial list already contains X, then appending it and then checking if it contains it again, it only gives us one piece of information that the append call actually doesn't remove X. And that's not very useful. So if you instead imagine that the append call is something that is going to take time, you don't want to always call it if your input space is not valid. So in those cases, we have a third case now. We don't just have to say true or no. We sometimes say I don't care. We say discard. The third thing is, as already said, you don't really like counterexamples. You want minimal ones. So the library, this is actually a good one. I have seen worse ones than this. So if you're just randomly generating stuff, trying to hit a bug, it is going, the examples that you're going to get is going to be very, very weird. So what you ideally would like is a way to minimize them. And for that, we change the running loop that I had shown you in the beginning a bit. We add an extra step of shrinking to it. So what we do is we generate check, and then we hit a bug. And at that point, we switch to a shrink check loop. And in this loop, what we do is we call these functions called a shrinker. And a shrinker is a function from a type to a list of items in the same type. And the shrinker's property is that all of those items that it generates are smaller than the original item. So here you see that for a list shrinker, we are producing two smaller lists. In the first list, we remove this first item. In the second list, we remove the last item. And in the second example, we are shrinking an integer by making it closer to 0, by just dividing it by 2, 3, or 4. So using shrinkers make the experience of property-based testing so much nicer, because you now get to actually work on examples that are interesting, that are inspectable, that are readable. The fourth thing is, this is kind of obvious, I think. You want some amount of configurability from your tests. So you want to be able to change the number of tests you want to run, the number of discards until you give up, the number of tests, you might want to be able to set a time limit for each single test. And you might want to be able to just say, okay, my time budget for all of this test is just a minute. And one thing that happens is, I'm just going to go into it in the next slide. some of the generators take take a size parameter, and in most of the libraries you're able to provide that from outside, so as to sometimes you want to test like you want to see really large structures, you want to generate really large structures, sometimes you want to test your stuff on small ones, and you of course want sensible defaults for all of them. So with that, we go into the systemic exploration. So here what happens is, I just talked about time, right? We don't want to randomly sample this input space all the time. We want to be able to do that systematically. And what we do is, typically, we first start with a very small small size to look at the small structures at the beginning. But as time goes on, you already exhausted your options on those, right? So you want to increase your size, and you typically do that by in a logarithmic sense. So the library also gives you that, and there is a fair bit of automation that these libraries do for you. The first of that is, given a type, most of the libraries are deriving generators for you. So this derivation is usually syntactic. It looks at the shape of the type, and it syntactically gives you a generator. And the things that you can derive are not just the generators. You can also derive shrinkers in some cases, in many cases. And if you have a Boolean function, then you can just derive all of this and turn it into a property. So here we start to go into the academic side, where we have things in the research community that mainstream libraries hasn't adopted yet. And one of that comes from my advisor's early work, in which they are using the inductive specifications of inductive relations in Cog theorem prover to derive better generators that can automatically pass preconditions. So here the type is a tree, and if you randomly generate trees, then they're not going to be binary search trees. But if you have an inductive specification of a binary search tree, which tells you basically the rules a binary search tree adheres to, then you can, using that structure, derive a binary search tree generator now that automatically passes the precondition, and this reduces the amount of work you have to do to a lot lower, because you usually have the inductive specification already when you're trying to write the generator. And a follow-up to this, which is even nearer, allowed us to merge these inductive relations. So now we can even automatically generate even more complex data structures, such as red flag trees, that we previously had a hard time with because their inductive relations are complicated. But now we can write small, simple inductive relations and merge them and get the generator. And there isn't really any mainstream approach to getting this into mainstream programming languages yet. But I know that there are a lot of people trying it by reverse engineering the structure of the code and similar. So in future we might also see these in general purpose programming languages too. So another thing we want to be able to do is have some control over what we generate. So I have first shown you an example of a generation where you're just randomly picking, right? But you usually don't want to be you usually want to be able to at least specify a seed, right? So how do you do that? And the way we do that is, our generators are actually lazy. They're not just functions that we are calling. And the laziness comes from the fact that you're waiting for the source of randomness, the RNG from the environment. And there is this thing called a splittable RNG, in which you take an RNG and then you split it into two independent parts. So now you can use it as if you have two different RNGs in which you actually have one. source of randomness. And using this approach, we can now fix the fix the RNG and get almost deterministic execution because we are generating the same examples all the time. But of course, we all know that we cannot really get deterministic parallel execution in all cases. But some people are trying to do that apparently. Well, good luck to them. And as we said, control, we also have new, more novel generation methods in which you can basically unwind the generator somehow, and you can go back, generate things, ungenerate, regenerate them. So generation is also a very hot topic in terms of research. And debugging, right? We want to really be able to understand what we're doing in code, and our tests are if your tests have a bug, if your generator is doing something that you don't understand, then that is a big problem because your whole premise of correctness depends on the correctness of your test in the first place. So you need to be able to debug the tests. And the first thing you do as this has been in Quick Check since the last 25 years, is that you can collect statistics from your tests. That is easy. That already existed. And in the last few years, now there is this trend of adding structured printing. Instead of just printing it all along, you can now have structured printing methods built into the libraries, so you can collect them from the outside with new tools, and you can create visualizations on them. You can create external statistics by processing them. And one of a leading work on this is Tyche. It is by Harry Goldstein. He was going to be here, he couldn't. And what Tyche does is it is already integrated to several property-based testing libraries. The first one is Hypothesis in Python. And what it does is you can now add events inside the hypothesis properties, and you can collect these events from Tyche and automatically generate the visualizations that I show you on the right. And this basically allows you to say, okay, my generator is good or not with respect to the property it's running. Whew. Performance. So it is very obvious. Faster tests are better. We run more of them. We can run them more times. And a very simple approach to doing this is you cache the failing tests. What you do is whenever a test fails, you put it to somewhere, and that is the first test you're running in the next test run. So if something already failed, it has a high probability of failing again. But there are other methods of making tests faster. One of this is very new. It was done last year, and what it does is it allows you to it allows your running loop to be async. You have multiple runners. They are picking up sizes from each other. And this gets you almost linear speed up with respect to the number of cores you're running it on. So this is very exciting. I love it. And the other is actually my work. We have last year published an evaluation platform for property-based testing. We have evaluated several property-based testing libraries and generators in Cog and Haskell. And later we now added OCaml and Racket. And we are working on adding more and allowing cross-language comparisons and stuff. So if you want a new language added to Etna, come talk to me. And the next, and I like this one very more, is guided property-based testing. So when you're randomly generating things, you can find bugs, but it would be even better if you could guide the generation towards interesting parts of the state space. And the first work on this was, I think it's on 2017. And in that work, you could give feedback functions to your property-based testing loop, and you could guide the loop towards that feedback function. And in the second work, again by my advisor Leo, they merged AFL-based fuzzing with property-based testing, So you can use the coverage information from AFL to guide your property tests now. And I will also quickly show you what the workflow, what the running loop for those look like, because I really like it. So the way it works is you have your generator, right? You have your checker, you have your shrinker. Those are already there. You add two new things. You first get a mutator, and a mutator is, instead of generating an example from scratch, it takes an existing example, it mutates it a bit. So now if you like an example, you can basically reuse it. And you also have a feedback function which tells you how much you like the example. And this feedback function in the fuzzing case is, it could be just the fuzzing feedback, the coverage feedback you're getting. But in a different case, I use this feedback as time, and we immediately got a performance fuzzer in which we could use the property-based testing loop to automatically detect, to automatically guide the input, guide the generation into inputs that are taking longer to execute. So you can do interesting stuff like that. And in this version, you first generate something, and then you call the checker with some feedback encapsulated on top of it. So you're getting feedback when you're running it. You can say that the function is instrumented. And depending on the feedback you get, you either generate or mutate. You check, generate, mutate, check, and shrinking is the same. There is a different version of this feedback guided loop in which you don't have to have an instrumentation, but you may get feedback from the result, like the input you're generating. And in this case, it could be that you may have some measure on your input that tells you if you like it or not. And yeah, so this is the same. You have the generator, mutator, checker, shrinker, and feedback. Okay, so these were the for the past 25 minutes or so, I've been talking about these different pillars of property-based testing, which I think what makes libraries good, what makes them useful. So and there's there's also things that I haven't been able to mention that didn't really fit into this framework. So I'll just quickly mention them now. Mica is an automated differential testing system that, given two OCaml modules that have the same signature, it automatically tests them to make sure that they exhibit the same behavior. And Harry also has a different work in which he talks with a lot of engineers from Jane Street to understand how they incorporate PBT in their lives. And he's trying to use those findings to make the PBT frameworks better. And in Do Judge the Test by Cover, again, Harry and Leo are investigating if we can run less tests with more diversity using combinatorial techniques in order to get the better inputs faster. In Falsify, we see that shrinking, like external shrinking, is not the only type of shrinking that you want. You can sometimes have different types of shrinking that is better. And in logarithm and program testing, we can the authors are basically showing that we can also test polymorphic programs with PBT, not just monomorphic ones. And in the last paper, we see LLMs can also help us write better properties. And I'll very quickly show my own work to you guys and then leave the stage. So in the last couple months, we have written a new property-based testing library that exposes these run loops that I have shown you in the slides as a user-level construct. So now you can write your own testing loops, and this allows you to combine all of these things and even more at the user space. So if you want to hear about this more, just let me know. And the key takeaways from my presentation is that first, we need the libraries, and second, the research is rapidly moving, and I think there's a lot that mainstream hasn't caught up to yet. I hope it will in the future. And also that the practice informs research in many ways. So we should talk more. Yeah. Thank you so much for listening to me. Oops. Yeah, question?
Maybe a weird question. Do you think that somebody could write prologue programs that would be written in a way that would make property-based testing redundant somehow?
Not sure. Like that looks like a long discussion. Maybe
Yeah.
let's take that offline.
Sure.
I'm curious to hear about that. Yeah.
That was the only thought I had about it.
I'll just from left to right.
So I'll second that last question by saying, I think that if you squint at inductive relations, they're kind of prologue programs. But what I wanted to ask was, in coverage-guided property-based testing, what we found in practice is that the default mutation operators tend to behave really poorly. And I was curious what the research community is looking at in terms of having better mutation operators for highly structured inputs.
So like we have actually looked into that. We have tried to get like by default like smart mutators basically. They weren't very good yet. But there are people working on that. I'm really hoping that it will be, because we know the techniques are working from the like generation from scratch work, right? So I think it's very possible that the mutation is going to have a similar like reach to a similar result. Yes.
Thanks. In my experience, the most annoying UX problem with doing property-based testing is that often the most interesting behavior in your code comes from having two inputs that are the same, or that one is a simple transformation of another. And so you end up constraining your input space to try to get that behavior, right, to be more likely, but that also means you're constraining your input space.
Yeah.
Are there good approaches to this in the research or in libraries that you know of?
So I think that's a very good point. Like we have a similar result in which in Etna, like the paper I mentioned, we do this experiment in which there is this folk knowledge that bigger structures are better because they contain more information, right? Like they have a lot more things to do, and that actually mostly checks out. In our 53 case studies, in 50 of them, bigger structures were better. But in 3 of them, bigger structures were exponentially worse because you needed the same thing in both cases. And if you're doing something bigger, then it's a problem. I think the work on combinatorial testing is good for that, because it looks into the generation problem as a problem of covering spaces. But I don't think people have a good characterization of those spaces yet. If you have a better characterization, then I think we could, instead of just randomly generating things, we could have these like generation blueprints in which one of those could be generating the same input twice in some cases. Yeah. Yes.
I was going to ask about the fuzzing, and I was really happy to see then you went right into that. But then you also earlier talked about kind of what is the role of the libraries, what is their part to play. So I wonder what sort of research is there with regards to making instrumentation for that fuzzing to help do that guiding better and easier for developers?
Not a lot, I would say, because like most of the work is just go straight to AFL, and because that's easy and it works really well. Like it's extremely performant to anything you would roll out on your own. So a lot of the times it just makes more sense to spawn a separate AFL process in the background and just get all the information from that. I don't know how that's going to change in the future. Like if there are better ways of spawning your own instrumentation on top of your own like language library. I am working on something for just instrumenting one function to see if like maybe you don't need all the information from AFL. Maybe it makes sense to just instrument small parts of programs and get information from that. But yeah, it's still a question, I would say.
Yeah, I was just imagine that that tighter integration on that one to make that easier.
Yeah. Thank you. Yes.
Yeah, I was just gonna ask, so I know there's some differences between property-based testing and model-based, and like model checkers like TLA plus.
Yeah.
So are there enough similarities to make this work, some of the most recent work here applicable to model checking?
There is a paper called Quickstrom. I think it's by, I don't remember. I'll just look it up afterwards. And they are testing LTL like specifications using PBT. So I think that is being done. Yes. Yeah. So do we have time? Okay.
Okay. So we talked about instrumentation for generation, which is really cool. But I'm curious on the shrinking side, are there any methods for incorporating feedback to determine good shrinking candidates?
I haven't seen any. Like I haven't seen any. Yeah. Because like usually the problem is shrinking is an explosive process, right? Like you're generating more and more and more of these things, and it's hard to determine which one of them is going to give you a better input, because all of them are giving you something. That's why you're shrinking it. If a leaf doesn't give you a counterexample, you stop shrinking on it, right? And even that is expensive. So if you try to add feedback to it, then I think that might be like too much computational complexity with respect to the results you're getting. Not sure. Yeah. Thank you.